Thank you. It's nice to come back to the fields. So I will talk about the generalized BDF theorem and Voiculescu theorem. Excuse me. So the first part of the talk, it will be very elementary, just see what these things are. So back to Weil theorem. So you have a separable infinite dimensional Hilbert space, H, and B of H, the algebra of all bounded linear operators on H. And let's say K is the compact operators. And it's an ideal. Suppose that T is a self-adjoint operator on H, then this is just one version of the theorem. So then there exists a diagonal self-adjoint operator D on H, and a sequence of unitary operators, such that it's approximately unitary equivalent to this diagonal matrix, and the difference all in compact. So it's compact perturbation. So that's the one version of Weil theorem. And this, so it took quite a long time. I think Edison once told me that people try for a long time to generalize the Weil theorem to this version of Berg theorem. It took quite a while. So we still have a separable infinite dimensional Hilbert space. And now T is a normal operator. Then what it says, you can also diagonalize in this way. So there is a diagonal normal operator D, a sequence of unitaries, UN, such that UN star TUN converge to D in uniform operator norm. And the difference is in compact. I guess I will not really talk about this process from self-adjoint operator to the normal operator. Then that's just in case. Well, let's say a normal operator means that you have it's commute with its adjoint, and diagonal operator just a diagonal, and the lambda are in the spectrum of D. And let's say pi is the quotient map from B of H to the Cartan algebra. And let's say T is an operator on H. And we use, so the essential spectrum of T is just the spectrum of the pi T. So in that way, we restate theorem like this. So H, a separable infinite dimensional Hilbert space, and you have two normal operators. Suppose they have the same essential spectrum, then there exists a sequence of unitary UN, and they are approximately unitary equivalent. And the difference is a compact perturbation of each other. This is just another version of the theorem.
You need the spectrum to be the same as the essential spectrum?
I'm not saying you really need. This is the way you stay together. Okay. You can have a spectrum which is not essential spectrum. They all have the same multiplicity and so on. They all will work. Let's not worry about these. Okay. Because I was talking about extensions. That's just for this way. And then let me mention one of the results from BDF from Douglas Fillmore. Okay. Let X be a compact metric space. H is just L2. And you have two unit homomorphism, phi 1, phi 2, from C of X, the continuous functions on X, to B of H. And we make sure that after you take the quotient, they are injective. Okay. Well, the pi is the quotient map. Then there exists a sequence of unitary UN. So these two maps are approximately unitary equivalent. And the difference is in compact. So in the quotient, they are actually unitary equivalent. Okay. This is another, just you can view this as a generalization of previous statements.
So in this second one, you want a P1, and that's so what? You have a P2 on both sides in 0, 7. So you add a P1, you understand P1.
1, 2 is 1. 1 over the 2 is 1. Sorry. Thank you.
What's the difference between this and the special case of Voiculescu theorem?
Yes, it is. I'm trying.
Okay, well,
Yeah.
you're saying that this is historical, Voiculescu generalized.
That's what I'm trying to say. I just say one version.
Well, okay.
Yeah. So this I think why theorem and Berg theorem, and one of the results from BDF theorem says this, and of course, then you have a Voiculescu theorem, and now H is separable. You don't actually need a unit, but just for the consistency, let's say it's unitary. And you have two homomorphisms, and then we assume in the quotient, the composition both are injective. Then there exists a sequence of unitary UN, and such that it's approximately unitary equivalent. And the difference, oh, this is good. It's a 1, the other is a 2. And the difference is incompact.
But why do you say uniform?
Then you don't need unit. I just get a consistent. Yeah.
But your homomorphisms must be unitary there, because otherwise one could be unitary.
Right. I think that's what I intend to say. It's the unitary, and it's a unitary homomorphism.
Okay, so the homomorphism is uniform.
Yeah. Unitary.
Right.
Yeah. Okay, so you look like these look like the generalization of previous one. But this is really just for any separable C-star algebra. Now, I want to go a little bit further. So let's say an operator T is essentially normal if in the quotient it is a normal element. So the question is, it's a very old question, is, okay, you have an essential normal operator. Is it just a normal, compact perturbation of normal operators? So that was one of the old questions. Let me try to explain this a little bit more, very elementary, but maybe to review something. So let's look at the example. Example, of course, is the shift operator. So you take in an orthonormal, say, not just orthonormal basis for En, and you look S is the shift, one side shift, and then you look what is the S star. S star has a kernel. Okay. So S star S is the identity, and SS star is a projection. And it's a miss E1. Okay. And you look at the difference is a rank 1 projection. So in other words, that this is unitary in the quotient. So in particular, it's essentially normal operator. It is a Fredholm operator. Roughly speaking, I mean, I don't want to go very far. To me, you just say the kernel and the co-kernel, they're all finite dimensional. Okay. If T is a Fredholm operator, then you have an index. Okay, so it's integer. So if you look at the set of all Fredholm operators, and it's a open set, and this map is continuous. The index map is continuous. So if you have 2 Fredholm operators, and then you have the product that's still Fredholm operator, and the index is you have this formula, so multiplicative become additive. And if you have a compact perturbation, then it's still a Fredholm operator, and you won't change the index. But if you take the star operation, you get the negative of it. So therefore, if T equal T star, then you compute that the index has to be 0. Yes.
It's just a bit part of action. Do you know who invented this index of a friend?
Who invented it for?
Well, you don't think it was Fredholm?
I don't know.
Well, I think we could assume go further in order to.
Right. Thank you. Thank you, Josh. And then it's you.
You know who he was a student of? Met Leffer. The reason I know is that I met a Swedish guy, bed and breakfast in Copenhagen, and when I told him that I was visiting the math department, he said, well, his uncle was a mathematician. Okay. Well, but I couldn't catch. He was speaking in Swedish, which I could barely understand. I mean, I could speak Danish, but so I got no idea at all. I just what his uncle's name was. Okay, but I asked him who his supervisor was, and he said Midnight Left. Okay, well later in the day I knew who his uncle was, because I had a vague idea of the pronunciation of the name.
Okay, good. Fredholm. And you compute the index of the shift operator is -1. Then S, the shift operator, cannot be written as a normal operator plus a compact. Now here you see it's much easier if you say it cannot be written a unitary plus compact, but I just say it's not a normal operator plus a compact. But then you do some polar decomposition, say n is normal, k is compact. If this actually happened, then this normal operator would have the same index as S, and then you look at the polar decomposition. Since n is normal and U is a normal partial isometry, it commutes with the absolute value of n, say, and you can compute what the U star is, and then you compute what the index look like. So that the index of U would be index of n, But U star U, U star, they're the same, it's normal. So it's a P, then of course you compute it, it's unitary, has index 0. And that's give you a contradiction. So index of n is 0, that would imply,
But then we have to argument.
which is 0.
Well,
It's a self-adjoint
no,
now.
come on. Once it has index at 0, but you have to check that it has an index. But okay, but you don't, it's not very hard, but I don't think you can.
Well, the product of two Fredholm operators.
Yeah, it's a
is Fredholm,
Fredholm.
so you can just multiply and do.
Well, that's half of a proof, but we didn't get even anything of a proof.
I didn't intend to give a full proof anyway, just said. Yes,
One of the technical points that I'm
right.
even referring to.
So of course, n is an absolute value, n is n star, and which is still Fredholm, and then you take absolute value.
Take the square root.
Yeah, take.
So we can do it, but I don't think we should just ignore it.
Okay. But anyway, so sort of convince you that when you have an index not 0, you're not going to write a normal operator plus a compact in this case. Okay. So this is a contradiction. So S cannot be written in n plus k. That's what I thought. That's why people think about the BDF theory. Start with something about whether an essential normal operator is a compact perturbation of normal operator. So now let's take a compact subset of the plane, and let T be an essentially normal operator with the essential spectrum equals X. Then pi T, maybe at identity, generates a C star subalgebra, which is isomorphic to C of X. And so, in other words, you have a unitary injective homomorphism from C of X to the Huaxin algebra. If, let's say, T equals n plus k, with the spectrum of n is X, then one obtains a homomorphism from C of X to B of H. So it's lift phi. When does such phi exist? Well, if you consider such a map from C of X to the Huaxin algebra, the homomorphism phi induces a homomorphism on the K1 level. It happened to be just integers on the side. And so it's kind of a Fredholm index. Then if there exists a phi lifts there, then on the K1 level, you also have this decomposition. Since we know K1 of B of H is 0, then this map has to be 0, which implies the psi on the K1 level is also 0. So let's return to the shift operator. So pi is a unitary, and the essential spectrum is the entire circle. And it gives you a unitary injective homomorphism from continuous function on the circle to the Huaxin algebra, defined this way. Then this psi star 1 as a K theory, K1 level, it's not 0. So that means so that things cannot lift. So BDF theorem, original version, so if X is a compact subset, and if I have two essentially normal operators with the same essential spectrum, then there exists a unitary U in B of H such that the difference of U star T1U and T2 is compact if and only if this index theorem, why there is a 2. 1 over 2 is, this is a 1. I'm sorry. Well, phi 1 is induced unit homomorphism by TI. 1, 2.
In the previous slide, I didn't see why you couldn't have an extension. Where did something go wrong?
That C1, C star 1 was not 0, and if you add the lead C1 star, it will be 0.
Okay, yeah. And then
Go back to the previous slide.
okay, but we're always taking things for granted that the K1 is non-zero. The K1 is a unitary.
Yeah, so we
I don't know how you decide what to tell us and what you think we already know.
so the separate joint, the shift operator, we sort of computed the index is not index is -1, so to the unitary in there, and we also
But why is it not equal to 0? What's our reference for the?
that's where we computed. I think it's a. Let's see. I think
But it's fairly typical in theory that the index.
so. We computed it's a -1. You look at the kernel and the co-kernel.
It's fairly sophisticated theory that the index is related to the K1 part. Anyway, probably some people in here have taken my course. No, when they take a dump course.
Let me back to here.
Again, I don't quite see what you assume we know, and what you assume we don't.
No, I assume you know. Just kind of review.
Okay, but I'm not quite sure what you're doing about it.
So just remind this.
Sounds like you're reviewing 50 years of mathematics.
Yeah, I just say, you start with the shift operator. We sort of know that the index is not 0. This map, this unitary is not in the Huaxin algebra. It's not connected to 1, and we all say you cannot be lifted, right? If let me say this: right, yes. And we sort of said that the shift operator cannot be written as a normal operator plus a compact operator. So maybe that is the way we know the unitary or the K1 map is not 0. So this is not,
That's sort of the basic.
yeah. So
Deep back with index from the K1.
right. So this is not going to be 0. We know, well, at least we know it cannot be lifted to a unitary or normal operator. So for the BDF theorem, here let me see. Okay, so T1, T2 are essentially normal operators, and they have the same essential spectrum. And the statement is that if they are unitary equivalent modular compact, if and only if they have the same index. K theory. And no, I'm not proving this, but this is kind of part of the theorem that you want to lift it, and the index has to be 0.
Okay, but I guess that's a consequence.
Yeah, this is a one consequence corollary. So this is
You
the,
want to now the start on the K0 group or is still on the K1 group?
this is a K1, this is one. Now you move this one to here, there are too many of them. Sorry. Okay. It also shown by BDF, if you have a two unit injective homomorphism and they are unitary equivalent, that is, there exists a unitary in the quotient such that they are unitary equivalent. The quotient is the same as a strong version that the unit on the top map down to get this unitary equivalence. I think this is a part of in their paper, so they don't really talk about strong or weak, so they are the same.
That's just true for the community case.
In particular, in the community case, if it's not community case, then so now let's look at the C-star algebra corresponding to the extension that is if phi 1, phi 2 are unit and strongly unitary equivalent, then these two C-star algebra actually isomorphic. So let me see. Yeah, I want to restate the theorem.
Sorry, which C-star is the right one?
Yeah, so there, yeah, there you have two extensions. You have a second one. And if these extension unitary equivalent, then in a strongly unitary equivalent, then E1 and E2 are isomorphic, in this case at least. Okay, so in this case, strongly unitary equivalent, same as weakly unitary equivalent. It's easier to see how you do a homomorphism, isomorphism. So with the Voiculescu theorem, let me just state the theorem here is that you can do better. That is, they are actually approximately unitary equivalent. So this is another version. I think now the 111, yeah, it's better. I don't remember it was actually stating the BDF theorem, but it follows from their theorem. So it's sort of classify these essential extensions of C of X up to this strong version of approximate unitary equivalent. Okay. Now let A be a C-star algebra. Consider the essential extensions like this. The Bousbet invariant view a homomorphism from C of X to the Cockney algebra. A. Sorry, I'm still thinking about the BDF theorem. It's A. Okay, let's ignore the Bousbet invariant line. The two extensions are unitary equivalent. If there exists a unitary U in the Cockney algebra, so that this they are unitary equivalent in the quotient. They are strongly unitary equivalent if this unitary come upstairs. Let me temporarily use this exit group. Is the unitary equivalence class of essential extensions of this form. So this is something I want to just mention because we will come back to this. So there is a theorem of Brown says you have this UCT of extensions. And then I, of course, come to the Kasparov theorem. You have a, let's say, a separable amenable system algebra. This extension group is same as the KK1, a K. So it's sort of solve all the problems. And even you can go beyond the K. But let me say, in general, let's say B is non-unital, but let's say it's sigma unital. And A is a separable system algebra. And extension is said to be essential. So let's ignore the one which is not essential. That is, nothing is orthogonal to the idea. So therefore, we were talking about multiply algebra. So the M of B, or idealized of B in the double star. And essential extensions are determined uniquely by the injective homomorphism from A to the clonal algebra. But again, this is just the Boole-Spain invariant. If B equal K, then of course the multiply algebra will be just all the bounded operators. And the clonal algebra is the Descartes algebra. So why we still want to look at extensions since we already have Kasparov theorem? Let's look at a special case. Let's look at a unital simple F algebra with unique tissue state and take an element which is not in the modern words, this is not Kunz equivalent to a projection. Okay. Then we look at a Hilbert subalgebra, make sure it is not unital. So this is non-unital simple F algebra. And let's use this notation for the pairing K0 to the traces. I'm not going to prove it.
Well, I mean, you can't just say it.
You
have to be different.
It must be, I think, if I'm correct, was that the Bratteri will first prove it?
By whom?
Ola.
No, it was simultaneously by Joachim Kunz and me.
Oh, okay.
And then the proof from turned out to be the same as the proof that if you replace AF by real line 0, it's still true.
Okay.
And so Brown and Peterson will mention that. And when they were talking about that, we could get them to the real line. It's a rather non-trivial.
No, yeah. Definitely. Okay, so anyway, we what we are looking at is a non-unital simple F algebra. I should really start a non-unital simple F algebra. So this is the pairing, or we think the K0 mapped to the affine functions. And then you look at the range of it, and that would be a dense subgroup of R. They all need to be proved. Okay, it's a subgroup, but why it's dense and so on. It's countable. Maybe it's easier to say it's countable, but you need to show it's dense. It's not always the case if C-star algebra does not have a real rank 0. Let me insist that this thing is not 0. Okay, the kernel of this map is not 0. That means K0 contains some infinitesimal element.
We'll forget about infinitesimal. You're taking it for granted that it's a finite number.
What?
Well, you're taking all kinds of things for granted. You have P is a projection, and tau is what is tau?
Tau is a unique trace. That's probably why I start with the unit to C-star algebra. Oh, did I do something wrong?
So you
Yeah.
had the finite trace. Okay.
Yeah, finite trace, yes. Yeah. Apparently I did something wrong.
You have to go back to full view, full screen.
What's the difficulty?
I cannot really read this.
Full view. Full screen.
Yeah, I guess I start with unit to just try to avoid why something is finite. So there are infinitesimal elements there. Then one has you compute a K0, you have this short exact sequence. And then you can compute K0 of the multiply algebra. It's just R. And then you choose a non-zero projection E in B1, and with some value, say D1. And then you take D2. So you have D2 is a smaller.
You know, you're making us work very hard on certain things that you mentioned. For instance, that B1 also has a unique efficiency.
B1 has a unique.
I know it's true, but I had to.
I'm sorry. So
That's where you are.
so it's A is a simple. So B1 is a stable isomorphic to B.
Well, that's non-trivial theory.
Right. One way to look at it is you have a trace, you have at least one trace restricted on that, and then you extend it to the whole thing, and then there's only one of it.
You see, why not just say that B1 be a non-unital algebra with a unique. One trouble is that it might have an infinite trace too. In fact,
Right.
That's still a problem. I mean, you're really thinking things under the carpet.
So I want to start with unit 2, let's just try to avoid the second question of yours.
I have to compute after I go home. I have to compute for half an hour.
Okay.
I'd like to see a simple main point that I don't have to make things for granted.
But okay, so I can say you start with a non-unital simple F algebra with a unique trace, if we agree such a thing exists, and then there's one.
It's ambiguous because unique bounded trace is not the same as unique
Yeah, so you choose one that is only one trace and it's bounded.
Okay.
Yeah, such a thing, and then it will then certainly will work. But we assume such a thing exists.
Why do you want it to be, is it clear why you want it to be an AF? Don't fit together?
No, yeah, I just what I'm going to say doesn't really need a AF algebra, but I want to have lots of projections, so you have some freedom
Yeah.
to choose these projections there. And you know, these is sort of dense, you can find those things. And then we fix a pair of projections in this corner such that the traces are the same, have the same value as D2. Okay, but we assume that the difference actually they are not the same in K0. Okay, so the difference is in the is a non-zero element in the infinitesimal element. Now I want to tensor with a K. Okay, so this is the to go to a larger algebra. And this is also a non-unitary separable simple F algebra, if you allow me to say that. And it doesn't change the K theory. Now, here is a easier fact that if you choose a element in D in the range projection, I mean a range of the K0, and with a positive element, then you can always find a projection which in the multiply algebra, but not in B, such that the trace equal that value. And if you believe me, and we say K0 of the multiply algebra is just R. Okay. And we want it orthogonal to E. Now the reason is B now is stable, so you can lots of projection outside. I have a little bit of computation here. So let's say K1 is Q01 plus Q00, and Q2, you add a different projection. Okay, they have the same trace. So therefore, in fact, you can find a partial isometry in a corner of the multiply algebra, such that V0 star V0 is Q1 and V0 star is Q2. So they are equivalent in the multiply algebra.
So you said you weren't proving anything, but this looks like proof to me, but I don't know what it came to prove.
I'm going to construct, I try to answer this question, why I bother to talk about extensions. We already have a Kasparov theorem. So I've tried to give an example, start with a simple AF algebra.
Example of what?
Examples will show you that Kasparov theorem is not enough for our classification or determine the extensions.
Yeah, but by now I forgot what Kasparov theorem you're talking about.
We just talked Kasparov theorem as the KK1 to identify with the exit group of the system.
No, I don't think anyone would try to quote Kasparov outside the realm of compound operators.
Well, if it's purely infinite, then it's just same as the KK1.
Sorry? Well, no, but you're not talking about Kasparov, you're talking about, well, okay, general Kasparov bivariate function, but that's, I think it could take a week to lead up to some non-trivial statements about that.
No, I'm not going to talk about the Kasparov theorem. I'm just saying why we want to revisit the extension theorem if we already have a Kasparov theorem to describe those things. So So I try to assure you have some extension by alpha algebra, and they have the same KK element or KK1 element, but they actually different extensions. Just look at some UHF algebra, or in this case, look the AF algebra with a unique Churchill state.
But did that surprise? I don't think Kasparov defined this function in terms of extension. Same extent, isomorphism of the thing.
Yes, as a group, they are isomorphic. What I'm trying to say is this group is not enough to describe extensions that we are interested.
Oh, but if it's that's in the Kasparov group is defined in terms of extensions in a certain way. That's one include. But you don't just take the extension. You take some kind of weak equivalence class. When you you don't have to talk about Kasparov. You can just say talk about extension. Then there are extensions that are equivalent in a certain weak way and not equivalent.
That's right.
But that's is that the main point? Is that the main point of this?
It could be. It could be.
Then it actually be the example.
So, the reason I want to give an example is seems that there is some sort of some people will think that extension, you have a KK theory, so why bother to look at it at all?
Why bother to look at what?
Why are we still worry about to determine what is extensions? They must be the same.
You're pointing out that the theory of extensions is a finer theory.
What I trying to say is that you in the previous case from BDF theorem and so on, if unitary equivalent, then C algebra isomorphic, so you use a KK theory to describe it. But that cannot be done in general. So there is reason to look something else to determine the extensions. I was at one point asked why you do that. We already know KK theory. Why are you talking about extensions? So that's one of the reasons that I want to mention this. But on the other hand, I will still use the Kasparov theorem to describe it, the extension, but in a different way.
Where does one talk about extensions without only being interested in the Kasparov theory?
Well, Kasparov has a theorem that says his X group is the same as a KK1. So people say, we already know what a KK1 is. Why you continue to talk about it? So I want to say that's not enough.
But I don't quite understand because KK1 is not just isomorphism class.
Well, there is a theorem says in this separate amenable case, they are isomorphic as a group. And that's
I don't quite understand. If the group that you define a group, you have all kinds of cancellations.
That's right. So that's the point. So the first part of my talk, I want to tell you that there is a reason to study non-stable KK theory for the extensions.
Well, just the reason that it's different from the stable one.
And that sometimes they are the same.
Sorry?
Sometimes they are the same. And in fact, I want to say we still use the KK theorem. It just not use the same isomorphism. Use a different one. Slightly different one, just different angle. I will show you isomorphic theorem.
By our schedule, we're supposed to take a break. Would you like to take a break now?
Oh yeah, let's do that.